This is Algebra 2 with Trig, 7a.3. Explicit sequences working with the geometric form. Notice that our geometric form is a little bit different. It's more exponential. So when we calculate our terms, a of 1 is going to be 3 times 2. We're going to do 1 minus 1. That gives us 3 times 2 to the 0 power. We know that 2 to the 0 power is a value of 1, so our answer is 3. So when we come over to our graph, we said that a of 1 was 3. So let's spend a moment talking about this equation that we have here. In this format, with the term n minus 1, the 3 is not your y-intercept. Okay, the 3 is not the y-intercept. The 2 is the ratio that we're familiar with. But because this is n minus 1, the 3 is not your y-intercept. It's the first term that we have in our sequence. If we plugged a 0, if you wanted to know what the y-intercept was, if you were graphing this out and wanted to know, you'd plug in a 0, which would give you a negative 1 exponent, which would give you 1 over 2, and would bring this down to a half. And then it would be 0.75. It would keep going down by a half. Well, we'll see that as we increase our n value, we get 2 to the first power, which is 2, times 3, which is 6. Now we're doubling the 3. We double the 0.75, we double the 1.5, we double the 3, now we're going to double the 6. So a cubed, or a, our third term, a sub 3, is 3, 2 to the third power minus 1, which is 3 to the 2 squared. So that's a value of 4. 3 times 4 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 would be approximately there. Just like we talked about yesterday, we would not connect those points. This is a discrete graph. We should not be connecting because we don't have values. We don't have position terms. We don't have n values between 1 and 2. We have 1, then we have the position number 2. We don't have 1.5, 1 3/4, 1.99. You can imagine that if we plugged in a 4, we should be doubling the 12. So this is going to be 3 times 2 to the third power, which is 3 times 8, which is 24. So the values that we're working with are twice as big starting with 3. 3 was kind of our starting point. So we had 3, then we doubled it to get 6, then we doubled it to get 12, then we were twice as big to get 24. So starting with that 3, we were getting twice as big. And the family that this would fall under would be called exponential. What we typically call an exponential equation in the past has been a times b to the x power. Notice that our equation is a little bit different. We'll talk about that here shortly. The exponent in a typical exponential doesn't have the minus 1, but when we do the explicit rule, we'll always have an n minus 1. So the explicit rule for a geometric sequence is a of 1 times r to the n minus 1. Notice how that's different than what we called our exponential here. The nth term of a geometric sequence, with the first term being 5 and a common ratio of 4. So we know a of 1 is 5 and the r value is 4. When we have the first term and we have the ratio, we are ready to write our rule. So 5 times 4 to the n minus 1. What difference, how are they different, do you notice between the previous exponential form, y equals a, b to the x, and the form for an explicit geometric sequence, which is a of n, a of 1, r to the n minus 1? Well, there's a couple different things that are different here. Not to mention the variables that we're using are a little bit different. In the original exponential, our a term was the y-intercept. A of 1 is not the y-intercept. That's one thing you need to be careful of. We still have the r and the b, that would be your rate. Of course, the exponent is what makes the a of 1, not the y-intercept. But that's the main difference. The exponent is n minus 1, and here the exponent is just the x. That changes what that value of 1 represents. So we're going to write a rule for the nth term of this sequence. Now this sequence is a little tricky because we get down into all these decimals. So we need to know a of 1 and the ratio. Well, we know the a of 1. That's 5. What we don't know is the ratio. So we can determine that ratio by looking at a term divided by the one before it, and a term divided by the one before it, and a term divided by the one before it. That should give us a common ratio if this is truly geometric. So here we have 2 divided by 5, and we got 0.4. Then we had 0.8 divided by 2, and we had 0.4. Then we had 0.32 divided by 0.8, and we had 0.4. So these all do simplify to the same value, which is exactly 0.4 every time. I don't prefer to use the decimals for this. We could do it as a fraction. We need to turn the 0.8 into a fraction. 8 over 10 would be 0.8. And we could do 32 over 100, and then we could simplify those down. But that shows us that we have this common ratio that is 0.4, or 4 over 10, otherwise known as 2/5. So to figure out our 8th term, notice we're at 5 for the first term, and then we're down to 0.2 and 0.8 and 0.32. So it's getting pretty small pretty fast, and it's going to continue to go down and be 40% of the previous every time. So to figure out our 8th term, we're going to start with our first term, which was 5, and our ratio of 0.4. And we want to know the 8th term, so we plug it into our formula is 8 minus 1. So since our first term was 5, we need to do times 0.4 7 more times. So this is 5 times 0.4 to the 7th power. And that gives us a pretty small number, 0.008192. So that's not overly surprising since we're getting smaller and smaller and smaller. This is 0.32. This is 0.00. So this is considerably smaller. If you don't know A of 1 and your ratio, just substitute the given information into this formula and solve for what you need. So one term of a geometric sequence is A of 4 equals 12. So that means 4 comma 12 with a common ratio of 2. So what don't we have? We need to know A of 1 and R. Well, R is pretty simple. The ratio is 2. But what is A of 1? We could come back here to the 12, and we could probably work backwards. We could figure it out. That would be a possibility. We can also plug it into our formula. A of n equals A of 1 times R n minus 1. So if we plug in 12, we don't know A of 1. We know the ratio is 2. We get 12 when we plug in 4. And then we minus 1. So we have 12 equals A of 1 times 2 to the 3rd power. That's 12 equals A of 1 times 8. So we have 12 over 8 equals A of 1. And that can be reduced. 4 goes into that 3 times. 4 goes into that 2 times. So we're going to get 3 halves. So now we know our A of 1 and we know our R, so we're ready to write our equation. 3 over 2, our ratio of 2, n minus 1. That would be our rule, and we can test this rule out. If you like to use a calculator, you could test this rule out. We have 3 over 2 times 2 to the, we know the 4th term should give us 12, so 4 minus 1 should give us the answer of 12. So that's a way that you can test your answer to see if it's making sense. Now, to make it a little bit more complicated, what are we going to do when we don't have A of 1 or we don't have, or and we don't have the R term? the ratio. We need to know A of 1, and we need to know the R. We need to know both of those. Right now, we don't know either one of them. We have this point at 3, negative 48, and we have this point at 6, 3072. So following that pattern, what would our first term be and what would our ratio be? So we're going to start out with our equation. A of n equals A of 1, R, n minus 1. We could call that negative 48. We don't know A of 1, and we don't know our R value. But we know we get negative 48 when we plug in a 3 for the n. So that's going to be negative 48 equals A of 1, R squared. So to get the A of 1 by itself, we're going to take negative 48 and divide by R squared to get our A of 1 by itself. So what we did is we took our first point, we plugged it into our equation, and we figured out what our first variable is going to represent. But it's in terms of R. So now we're going to go back. We're going to bring down our new equation, 3072. We have our A of 1, which is negative 48 divided by R squared. That's our A of 1. We still don't know our R value. To the 6 minus 1. Well, 6 minus 1 is 5. So this is negative 48 over R squared times R to the 5th power. Now what we can do here is reduce, as we have in the past. The R to the 5th power would be on top of the fraction, and R squared is clearly on the bottom of the fraction. So when we simplify that, we get negative 48 R cubed, because we have 5 on top and we have 2 on bottom, and when we subtract 5 minus 2, we get 3. So now we're going to come through and divide 3072 by 48. That gives us negative 64, and this is starting to work out. If we have R cubed and have figured out that that is negative 64, we can take the cubed root of both sides, and that's going to give us an R value of negative 4. So we know our R value now is negative 4. But what don't we know? We don't know A of 1. So to figure out A of 1, A of 1's right here. A of 1 in terms of R. I can do that. So I'm going to bring my A of 1 that equals negative 48 R squared. So A of 1 is going to be negative 48 negative 4 squared. So A of 1 is going to be negative 48 over 16, which A of 1 equals negative 3. Phew! We did it. What did we do? We took our first point and we plugged it into our geometric, and we got A of 1 by itself. Then we took our second point using this new a of 1 and the new point to figure out what the actual value of r was. And we could use that back in to figure out a of 1. So a of 1 is going to be -3. So our final answer is a of 1 times r to the n minus 1. Not a simple one, but we've done this process in the past, specifically when we were working with exponential equations. All right, this is a U try. So you can pause the video, you can work through number 1, A and B, and you can even work through 2 and 3. And then you can come on back and we'll work you through it. All right, write a rule for the nth term. Here's our sequence. So you may notice we need to know, we've done this several times now, we need to know what a of 1 is. Well, that's obviously 4. And we need to know what our ratio is going to be. We can figure out our ratio by taking our number divided by the 1 before it. Take your number divided by the 1 before it. And take your number divided by the 1 before it. That's going to be 5. You can probably just look at it and say 4 times 5 and 20 times 5 and 100 times 5. Either way, r is 5. So we know our rule is going to be 4 times 5 to the n minus 1. So to find a of 7, we're going to say 4 times 5 to the 7 minus 1, which a of 7 is going to be 4 times 5 to the 6th power. Four times 5 to the 6th power. So a of 7 is going to be 62,500. One term of our geometric sequence is here at 3, -2, and our common ratio is r, is 3. We need to know what a of 1 is and what the r is. Well, we know what the r is. It's 3. We don't know what our a of 1 is. But what we do know is we get the answer of -2 when we're solving for our first term, and our ratio is 3. And 3 minus 1. These are different 3's, of course. So this is -2 equals a of 1, 3 to the 2nd power. -2 equals a of 1 times 9. So this is -2/9 is a of 1. That's kind of funny looking. So your rule is going to be a of n, -2/9 times 3 to the n minus 1. And you could test that out. You can take -2 divided by 9 times 3 to the 3 minus 1 power, and we should get the answer of -2. That worked out perfect. The last example here, two terms of a geometric sequence are these guys. So we're going to start with a of n equals a of 1 times r n minus 1. So let's plug in our smaller values, like that better. So negative 4, we don't know a of 1, we don't know r, but our n value is 2. So when we divide by r, this is r to the first power, so it's just r. So negative 4 over r equals your a of 1. Now we're going to take our second point, negative 1024. Our a of 1 is going to be negative 4 over r times r to the 6 minus 1. That's negative 1024. And this is r to the 5th power. We can reduce those. What do we get when we reduce r to the 5th power divided by r? That is r to the 4th power. So we'll divide both sides by negative 4. Negative 1024 divided by negative 4, and that gives us 256. Now that's 256 to the 4th power. How do we figure out what r itself is going to be? We have to take the 4th root of 256. So you can type in a 4 into your calculator. We've learned this before. Hit the math button, go down to number 5, and that makes it a 4th root of 256. That gives us actually the number 4. What that's telling us is 4 times 4 times 4 times 4 is going to be 256. So now we know what r is. We almost know what a of 1 is. Negative 4 over 4 equals a of 1. So negative 1 is a of 1. And we can use these to write our equation. A of 1 is negative 1 times r to the n minus 1. That is a little complicated. Think about what we're doing. We're starting out with our formula. We plug in our first point to figure out a of 1. We take our second point and we figure out r. And then we plug it back in for a of 1 so we can write our equation. All right, last story problem. In 1990, the total box office revenue at the U.S. movie theaters was about $45 billion. From 1990 to 2003, the total box office revenue increased by 5.8% per year. What family of functions best models a situation when a quantity increases or decreases by a percentage? That would be exponential. Write an explicit rule for the box office revenue. Well, a of 1 is going to represent our 5,000.02. And our ratio, how is this changing? All right, our instinct is to say that it's changing by 5%, 5.8%. But it's changing by 100. So we've got to move the decimal spot. over twice and put a 1 in front. It's 1 plus 5%. We don't want to know what 5% of 45 million is. We want to know what 100% and 5 extra percent is. So our A of n's going to be 45.02 times 1.058 to the n minus 1. An explicit rule, you would need to know where we're starting with, 45.02, and then you have to write out the pattern of what's happening. We're starting out with this 45.02, and we're changing it by 0.058 n minus 1 times. Hang on. No. Sorry. I jumped the gun here. Yes, that's our value here, but let me start this one, that little bit over again. Our recursive rule, sorry about that. Our recursive rule, recall, is the ratio, which is 1.058, times our previous term. There we go. That's more of a recursive, remember, has to work with the previous term. To find our fifth term, we don't want to have to find our second and third and fourth term. We can go right into 45.02 times 1.058, 5 minus 1. 45.02 times 1.058 raised to the 5 minus 1. And we get 5641. And that is billion. Now let's try our other formula here. Let's try starting with 4502 and timesing that by 1.058. That would be our second, our third, our fourth, and our fifth. And that was our fifth one. That's what we wanted. So the numbers come out the same. Either way you want to do it. It's definitely easier to use the explicit rule. Okay. So we can do one calculation.